Okay, we have the fundamental theorem of calculus, part 1. So assume we have f at x, which is continuous on a closed interval from a to b, and uppercase f at x is the antiderivative of f at x on a and b. Then we can calculate the definite integral of f at x from a to b by performing this calculation. The antiderivative at b subtract the antiderivative of a. This is a calculation that we've done in the past, very familiar with it. So this video is about technique and applying this theorem. And below here I have a whole bunch of helpful formulas that you may want to pause the video now and maybe jot these down on a piece of paper, because these will be helpful in evaluating definite integrals. So here's our first example here. We have the definite integral of 4x minus x squared from 0 to 5. So let's calculate the antiderivative on the side here. So the antiderivative of 4x, add 1 to the exponent, divided by that exponent, we get 2x squared. And x squared has come up a lot, so that's one I know by heart by now. And that's it right there. So we're going to use that in our calculation here. That's f at 5 minus f at 0. So f at 5. Oh, here's a good point in the video where I can show you another notation that is very helpful. So this is the antiderivative. So what we'll do is we'll just write it down. 2x squared minus 1/3 x to 3. And we'll draw a line here, and what we'll do is put the 0 here and the 5 there. So this is a notation. We could have skipped this line here. We're just so used to using this line that I wrote it down. But we can skip this line now and just jump to here. So write down the antiderivative expression here, and then a line and from 0 to 5. And then perform your calculation. Substitute 5 for x. And then we subtract. Substitute 0 there. And that's going to be an easy calculation because that's all going to be 0. So this is all going to be 0. So we just have to worry about this. So this is 5 squared, 25 times 2 is 50. 5 cubed is 125 over 3. We need a common denominator here. So that's 150 over 3 minus 125 over 3. And we get a final answer here, 25 over 3. Here's another example. This time we have to determine the antiderivative of cos, which is sine, but we have cos of 1/3 theta. So here, the antiderivative of cos 1/3 theta, here's a formula you should memorize. So if you have the antiderivative of kx, some constant times x, the antiderivative will be 1 over k sine kx plus c, a constant, because that's the indefinite integral. Here we have a definite integral because we have limits here from 0 to pi over 2. So we'll just use this formula here. It'll be 1 over, now the constant's 1/3, so 1 over 1/3 sine 1/3 theta from 0 pi over 2. Let's simplify this. This is 3 sine 1/3 theta from 0 to pi over 2. So we substitute 3 sine 1/3 theta. Now theta is pi over 2. And we're going to subtract 3 sine 1/3 of 0. More simplifying here, 1/3 times pi over 2 is pi over 6 minus 3 sine 1/3 of 0, 0. Okay, so let's calculate this without a calculator. Pi over 6 is 30 degrees. So we'll use our triangle here. I like to draw it. 30 degrees is here. 1 is across from 30. 2 is across from the 90. And pi over 3 is over here. So the sine of pi over 6 will be opposite over adjacent. That's 1/3. So 3 times 1. Sorry, 1/2. I meant 1/2. Subtract 3 times the sine of 0 is 0. So we have just 3 over 2 left over. Final answer. Okay, so here's another one. The definite integral of dx over x. Now that may look confusing to you, so let me just rewrite this. Also, from a to 5a. Let's put that up here, 5a. So dx over x is the same as 1 over x times dx. Okay, so that should help a bit because the antiderivative of 1 over x is ln of the absolute value of x, and this is going to be evaluated from a to 5a. So we just substitute here the ln of the absolute value of 5a minus ln the absolute value of a. Okay, so let's continue up here. Let's use some properties of logs. The difference of logs is the ln of the quotient of the two. So in this case, the quotient here be 5a divided by a. And let's continue here. We'll rewrite top here as 5 times the absolute value of a over absolute value of a. So all I did is take the 5 outside the absolute value sign, and 5 is positive, and that's no problem here. And absolute value of a divided by the absolute value of a is 1, so this simplifies to ln 5. The fundamental theorem of calculus has a part 2 to it, and here it is. You may want to pause the video and give this thing a read. Let me just explain it briefly. What this is saying is that if you take the derivative with respect to x of this integral, you get back to the original function that's in here. But this is f at t dt, and where did the x come from? Well, when we do our substitution with the antiderivatives, we'll have our, let me write this out. So let's work out the integral here. That's capital F at x, subtract capital F, that's right, those are antiderivatives at a. And then when you take the derivative, you use like a distributive property here. The derivative of, with respect to x of the antiderivative here, we get back to the original, which is f at x. And when you take the derivative of this number, now this is a number, it's constant, and the derivative of constant is 0, so this disappears. So that's what's happening here. This part of the theorem is just making the connection between two branches of calculus, differential calculus and integral calculus. And the connection between the two is if you differentiate the integral, you get back to the original function. So that's what this is saying, just very briefly and very quickly. So let's work out some examples. So let's apply part 2 of the theorem to this example here. We have some function here, and it's equal to the definite integral of the square root of 1 plus t cubed from 2 to x. So just, and we want to calculate a prime of 2. So let's figure out what a prime is first of x, a prime of x. And using the theorem, all it says is that we can just rewrite this function here and just put an x in there. So here you go, 1 plus x cubed. So that's what the theorem states, and we're applying it here. So if we want to figure out a prime at 2, all we need to do is just substitute 2 in there for x. And 2 cubed plus 1 is 9. Square root 9 is 3. There's a very simple application of part 2. Okay, one more example of applying part 2 of the theorem. We want to figure out g prime at x. And g of x is this definite integral of sine t dt. But this time we have a number here as we did before, but up here we don't have x, we have x squared. So you may be tempted just to say it's sine x squared, but that's not the case, and I'll show you why here. So let's differentiate both sides of the equation here. So with respect to x, so this is g prime at x is equal to, we'll differentiate this side here, from -2 to x squared sine t dt. So the antiderivative of sine t is negative cos t. Negative cos t evaluated from -2 to x squared. Let's continue here. Let's work this out. This is going to be negative cos x squared minus negative cos -2. So now let's differentiate here. When we differentiate negative cos x squared, we get, with respect to x, we get sine x squared. But using the chain rule, we're going to have the derivative of x squared is 2x. And then when we differentiate with respect to x of this constant here, it disappears and you get 0. So here we go. G prime at x isn't just sine at x squared. You have to multiply that by the derivative of x squared, and that's 2x.